Hello, welcome back. Today our lesson is called mole ratios. This is lesson 4 in unit 5. So in the last video we talked about conservation of mass and how to determine missing pieces in a reaction. And so today we're going to kind of further apply these balanced reactions and use them to calculate mole ratios by using dimensional analysis. So this sounds really complicated and really scary, but let's think about it like this. So think about you're making s'mores. And so the perfect s'mores can be made with 2 graham crackers, 8 mini toasted marshmallows. So we add my other 4 right here. And 1 square of fancy chocolate. Now we can represent it in a chemical reaction. So you have your 2 graham crackers, so these are your GCs. You have 8 mini marshmallows, these are your MMs. You have 1 chocolate, and out pops this lovely compound. So GC2, so 2 graham crackers, 8 mini marshmallows, 1 chocolate, and that is, s'mores. Okay, so you get your graham cracker, you got 4 of those, plus your chocolate, 4 more, so 8 total marshmallows, and your thing. So that seems pretty simple, and again, here is your recipe. You can turn your recipe into a chemical equation. So now that we've done that and this equation makes sense, let's think about what would happen, or what would you need if you wanted to make 3 s'mores. So you have the recipe for 1, but you want to make 3. And she might just be like, okay, well, I need 1 chocolate for 1 s'more, so 3 s'mores, 3 chocolates. Totally correct. But I'm going to show you how to use it with dimensional analysis, so when we get to other compounds and scarier numbers and scarier units, we're not talking about chocolates and marshmallows, it still makes sense. So again, with dimensional analysis, you're starting with your given. So we're given 3 s'mores, and remember, this compound right here is your s'mores. So I'm going to use the fancy chemical formula for it, MM8CH. What do you do with your given? You put your given over 1. So we want s'mores to cancel, so we put them on the bottom. So GC2, MM8CH. And we're looking for chocolates. So chocolate is CH. So that's how the setup is set up with the units. But let's look at the numbers. Well, like, what number goes here? And so here's where the balanced equation comes into play. So you have 1 in front of chocolate. So that number comes there. And then you use the coefficient for this one, which is also 1. And so these numbers right here are the coefficients from the balanced equation. So now you're left with 3 times 1 over 1, which is 3 over 1, which is 3 chocolates. And you could have been like, well, duh, I knew that 5 minutes ago. Why do we have to do this all? And you shall see. But yes, that's it. Okay, so let's work on one more s'mores example. Let's say you had an unlimited amount of chocolate, unlimited amount of graham crackers, but you only had 1 bag with 100 mini marshmallows. That was it. That's all the store had. How many s'mores could you be able to make? And so here is our given. So 100 mini marshmallows. Put your given over 1. You want marshmallows to cancel, so it goes on the bottom. And we're looking for s'mores. Again, I'm going to use this fancy chemical equation for s'mores because why not make things look more complicated? Okay, so there's our setup. We want this to go on the bottom so it cancels. And so now we got to add our numbers. So 1 is the coefficient in front of our lovely s'more compound. And then 8 is the coefficient in front of mini marshmallows. So again, we're just taking the numbers from the given balanced equation. So now we're left with 100 times 1 over 8. So 100 over 8, which gives us 12.5. Remember, our unit is that. I'm just going to write s'mores because it's easier. So if you had 100 mini marshmallows, you could make 12 and a half s'mores. And so that's basically it. It's just thinking about a recipe. What do you have? And then what would you need to make a specific amount? And so that is what a mole ratio is. So using the cooking example definitely helps a lot because you've made something in your life before. Even if it's a simple sandwich, you know if you're going to double the making two sandwiches, you need double the amount of stuff. And so mole ratio is literally just doing that, but instead of marshmallows and chocolate, it's talking about compounds. And so when we're dealing with mole ratios, a mole ratio really is the ratio between reactants and products. And it's that balanced equation coefficient that tells us the ratio. And again, when we're using gases, we can use that number to represent liters. So in this chemical equation, what is the mole ratio of H2O to H? So if we're looking at coefficients, coefficient for H2O is 2. Coefficient for H is also 2. So we can simplify this. Simplify to 1 to 1. So our 1 to 1 ratio is what it would be. So if you're setting up an equation or your dimensional analysis and you don't simplify your ratio, that's fine. Doesn't matter. The math will simplify it for you by the end. But if you're given a multiple choice question, which you'll see in class, the answer choice will be simplified. So if you're like, oh, well, it's 2 to 2, and that's not an option, or whatever you see isn't an option, just make sure that you do simplify it. Okay, so let's kind of jump into a question with this. So here are the steps, and we'll leave them off to the side, but it's literally just like the s'mores example. But instead of, again, marshmallows and chocolate and graham crackers, we're dealing with H and O2 and water. So here is our balanced equation. Here is what we're given. So given the balanced chemical equation, how many moles of O2 are produced from 6.2 moles of H2O? So these questions sound really complicated. They sound really hard. And believe me, when I was in your shoes and even in college, I was just like, what is this? How do I do this? But when it finally clicked that, hey, dimensional analysis works wonders, that's when things became easier. So don't take these shortcuts because, oh, you think you get it. It really does, help. Okay, so our given is 6.2 moles of H2O. Put your given over 1. You want moles of H2O to go away, so it goes on the bottom. And we're looking for moles of O2. So there's our unit set up. So I'm going to add our numbers. So for O2, there is no number, so we have that invisible 1. And then for H2O, you have that 2, so the 2 goes there. And so you're left with 6.2 times 1 over 2, so 6.2 over 2, which gives you, these cancel out, 3.1 mole of oxygen. And so again, you might be thinking, oh, well, I make double the amount of water, so I need half the amount of oxygen. Again, you can sometimes kind of picture this into your head if the numbers are nice. But doing this dimensional analysis way, I promise you eventually it will click if you follow step by step by step the way I'm showing you. Okay, number 2, given the balanced equation below, what is the volume of C8H18? Change that to an 18. Will completely react to produce exactly 36 liters of H2O. Okay, so all of these questions may be worded a little bit differently, but they all function the same way. So here is our given, 36 liters of H2O. So remember, we can use these numbers as moles of something or the liters, because there is that relationship between moles and liters. You don't need to convert between them, but that does exist. So that's why we can use liters. So we're given liters of H2O. We want liters of H2O to cancel. And we're looking for volume. So again, volume is liters. Liters of C8H18. So there's our setup with the units. Let's fill in our coefficients. And so for this, our coefficient is 2. And for H2O, we have 18. So again, we can simplify this to 1 and 9, but if we're plugging into a calculator, it does not matter. So basically, you're left with 36 times 2 divided by 18, and you can totally try it this way. You could try it 32 times divided by 18, or you can do it as 36 divided by 9, both of which will give you the same exact answer, which is 4 liters of C8H18. And that's it. So again, it's just dimensional analysis, pulling in the coefficients from the balanced equation. So let's just do one last one together. Given the following balanced equation, how many moles of magnesium are needed to react with 3.7 moles of O2? So our given is 3.7 mole of O2. Put your given over 1. You want moles of O2 to go away. Moles O2 goes on the bottom. And it's looking for moles of magnesium. So mole of Mg. So again, there is your setup. And so now let's add these coefficients. So 2 in front of magnesium. And then we're going to put that invisible 1 in front of O2. And so remember, moles of O2 cancel out. You're left with what you're looking for. So you get 3.7 times 2 over 1. So you get 3.7 times 2, which is 7.4 moles of Mg. And that's it. Again, these questions look very complicated. They do, not gonna lie. But if you break it down simple steps like this, it is very, very manageable. The hardest they can make it is that they tell you to balance the equation and then use those coefficients. But that's literally the hardest it will ever be asked, and most of the time they don't put both of them in the same question on an actual test. Okay, so that's it for this lesson. That's it for this unit. Stay tuned for other unit review videos. On that note, have a wonderful day.